Okay, so the limit is the y value a function appears to approach. Appears to approach, and that term appears is very important for when we're working on this graphically, because graphically finding limits is a very visual thing. It's what it appears to approach for both the left and right hand side of a given x value. And when we talk about limits, it looks like this. It'll say, I am looking for the limit as x approaches some number. I'm just going to put a in for any number of a given function. That's a limit statement. I am looking for the limit as x approaches a number for a given function. And it is just simply what the graph appears to be approaching on the left and on the right. When it comes to finding limits, truthfully, the easiest way to find a limit is to plug a value into a function. Because if the function itself is a continuous function, meaning there are no breaks, no holes, no anything that's blocking anything, no asymptotes, the limit of the value will be the same, okay? But there are issues where there are breaks and holes and things where the limit and the value may not be the same or may not exist. So I'm giving you some pictures of different types. It's actually the same or similar looking function, just pieces are kind of moved or pulled out. I have an upside down parabola. And when I write my terminology in this fashion, this means I want to know what the value of -3 is. And so I go to the left -3 and up to the function that is the point -3 comma 4. And so the value is 4. Because this is a continuous function, again, continuous meaning no breaks, no holes, the limit is also 4. Because on the left-hand side and the right-hand side of that point where -3 hits the graph, it goes to that position. And I'm just trying to pinpoint. Sometimes I'll draw these little arrows on each side. Where does it look like it's headed? If I could walk up the graph on either side, I'm headed to that exact location. So the second one in that example is a little bit different. It looks like kind of the same thing, except for they removed the actual value. So when I talk about what is the value, it is undefined at that location. There's a hole. It doesn't exist. But to each side of that hole, the graph actually moves up towards that hole, right? On each side, it is surrounding that hole. And that means that my limit is 4 again. So here's an example where I don't have a value, but I have a limit.
I don't really like this.
It gets, okay, it does. You don't like things when we start, and then all of a sudden you're like, no, this isn't bad.
This is terrible.
It's not, I promise you. Okay, so on the next one,
It's different.
there's a little bit of a difference again. On this one, we put the value in there, but the value is not where the hole is. Okay? So, what is the value on this function of -3? 1. Because that's where there's a solid point. But what is the limit? 4. Why 4? Because the limit is not always the value. The limit is where it seems to be going on both sides of that point. And every part about the function is leading me up towards that top position, which is a y value of 4, even though there is no value there. So I can have no value at all, or I can have a value that's not the same as where the graph seems to be going. These are called holes, and we call this removable values, meaning I have this value that is outside of what everything else seems to be following, okay? Now on my next, it flips it over. What is the value at -3? Where is there a solid dot? That's at 1 again. How come it's not at 4? Because there's a hole there, right? Okay.
2.5.
Now, my limit, I'm going to go back up to my definition of a limit. It is the y value that the function appears to approach from both the left and the right side of a given function. Meaning that when I try to find my limit, I have got to come in on both sides, and they have to come together.
What?
So I look at this problem on the left-hand side, coming in from the left. If I could divide a line here, I have a left side and I have a right side. And on the left-hand side, it's going up to 4. On the right-hand side, is it going up to 4? No. It looks like it's going to 1.
It's going way down.
Yeah, it doesn't.
Whoa.
They, wait, whoa,
It's
whoa,
going
whoa.
away from 1.
Well, no, I have to do, yeah, this is gonna be the hardest part to get used to. I have to try and hone in on that point. So even though I normally read from left to right, I've gotta come in from the right-hand side and the left-hand side to see where they're going. So this one, if I'm coming in from the right-hand side, I follow this graph down, it lands here. On the left-hand side, I follow it up, it lands here. Do they meet? No. If they don't meet, I do not have a limit.
Oh, that's good.
And this is how we defined a limit that does not exist, is just DNE. You might remember Mean Girls when she said, the limit does not exist. Do you remember that? Do you remember that? Yeah.
Yes, I remember that.
That's what she's talking about. The limit does not exist. It doesn't go to a specific place. We should.
Oh, horizontal.
Yeah, we should. Okay, how about here? What's my value? 2. What's my limit? DNE, it doesn't connect, it doesn't go together. Now that I've said about a limit in general, we can break our limits down into 2 sides. And sometimes finding two-sided or two one-sided limits is helpful in determining whether we actually have a limit or not, especially when we get into piecewise functions. Because I want to see where it's going on the left, and I want to see where it's going on the right, and I want to see if it's going to the same place. And so that brings me into my one-sided limits. A one-sided limit is, again, still the y value that a function approaches as you approach a given x value. So I'm always thinking about the point of the location where I'm headed. I'm going to go towards an x value and see what y value it lands at. And this is from either the left or the right. The one-sided doesn't take both into consideration, it takes one into consideration. And I can have a limit as something approaches the left-hand side, and I can have a limit as something approaches the right-hand side, but I might not have a limit in general, okay? So there can be a value if I'm trying to get to 2. I can have a left-hand limit, I can have a right-hand limit at 2, but I don't have a limit actually at 2. Yes, what was your question?
Oh, nothing.
Are you sure?
Yeah.
Okay. So when we talk about left and right-handed limits, we show them with this little sign here. That negative means from the left. This positive means from the right. And again, that's going to be kind of the hardest thing that we have to get used to when we're talking about coming from the left and from the right, because I am going to come in from the left and to a position and come in from the right to a position and check to see if they meet. All right? So when I look at this picture, I have from the left, as I travel on this function from the left, I land at -1. And I come in from the other side, from the right, as I travel in that function from the right, I land at 2. And if I were to ask you, what is the limit of this function as x approaches x approaches 3. If these two numbers are not the same, we say it does not exist. And so that's how I use those one-sided limits to help me. I check it on the left, I check it on the right, I see if I get the same value. If I get the same value, then I know I have a limit.
Wow.
If I get a different value, I know I don't.
I really like this. I don't know.
So we're going to try some on a graph. Let's see how they go. We'll try these together, see if you can figure out our limit, and I'll talk to you about some little tricks and things that we can look at. So in this particular first graph here, my first area of interest is at -2. And what I usually do, I'm going to get myself an erasable marker so that I can erase it. Let's see if this will do. This might work. I don't know. We'll see. Okay, so what I like to do is I like to figure out what I'm interested in. I'm interested in -2, and I draw this kind of line down here. I call that my wall. And you don't have to physically draw it on your paper, but I always mentally visualize this kind of wall here that's creating two sides of this graph. This is the left side. This is the right side. Okay? And in the left, I come in this way. In the right, I come in the opposite way. And I want to get closer and closer and closer to the y value of the function. Not the coordinate plane. The coordinate plane is just what the function's laying on, or resting on. I want to get the y value of the function, so that's the drawing part of it. All right? So, the first one says, find the limit as x approaches -2 from the left. So that means I'm going to follow this graph, follow this graph, follow this graph until I hit that wall. What's the y value? 1. Beautiful.
Oh,
Okay?
so this would like a problem will look like is this?
Mm-hmm. Yeah. Yep.
What is this?
Yep.
What is that plus sign? Comes from the right.
Then that means it comes from the right. Yep, so I'm coming from the right. Now, there's a whole lot of activity that can happen on the right-hand side and the left-hand side of the function, if you notice. If I start on the way over here, right-hand side, I would go up here, come down here, I have to jump over this hole. I've got this value down here, I'm going to ignore that, but I want to get to this wall.
Is it the only?
And that wall stops at what value of y?
Negative.
-2. And then to answer your question, are these two the same? So that is it DNE? It is DNE.
Wait, whoa.
Wait, whoa.
So if there's no plus or minus, there's just the overall negative?
Yep,
Wait,
yep.
okay, what did
Yep.
we do on C there? So C is just like the overall negative too, you know
Yep.
what I mean?
So C is
Oh,
me
they don't
deciding,
meet?
do
They
they
don't
meet?
meet?
Yeah, they
Oh,
don't.
well, that's-
One stops, one stops
So if they
whole
meet,
here and
if
solid
they
here.
meet at a solid point. then-
Not a solid even, they just have to meet, which is this next one.
So if they met at like an open dot, that's the answer.
That's the answer, even though it's not the value.
That's
Yeah.
the answer.
How did you get -2 for B?
Because, again, if I'm coming in on the right, here I am following this function, following this function, I hit this wall. What's the y value at this wall? Yeah. Even though it doesn't exist there, I don't care. Don't mistake a value for a limit. They are not always the same. They can be. But why would we have a whole nother word for something if it was exactly the same as a value, right? So the value and the limit can be different. Yes?
What are you doing?
So now I'm going to get rid of this wall that I made.
Whoa.
I haven't used this in a while, so it left a little mark, but that's all right. And I want to discuss value because I'm not talking limit anymore. So I want to discuss value, and please, again, don't mistake the two. What is the value of -2?
The value.
Yes,
Well, how do we find?
1. Are you magic?
The value?
Why is the value 1? I agree with that 100%. What does that mean, the value?
It's the y.
That's the y value where it's a solid point. Yep. How come I didn't say it was -2? Because that's an open circle. The y value doesn't exist there. Where is it solid? It's solid here. Yeah.
Can it be solid in 2 spots?
No, then it's not a function. that it fails what we call the vertical line test. You kind of remember that? Yeah, so it won't be solid in two spots. Yes?
How did you know that it's not like the negative, so like the whole dot that we were working with last time?
Mhm.
How do you know it's not that one versus the other negative two one?
How do I know it's not this?
Yeah, or
Be-
like either or.
Yeah, because I'm eyeballing at -2.
Okay.
So there are two things on this function at -2. There is this point, -2 comma 1, where I have this nice solid dot, and there is this point which is -2 comma undefined, where I have a hole.
No.
Yep. I'm not using that one because I need to be at -2.
Oh,
This one is 1 something,
okay.
and I'll use that when I'm trying to find the value or the limit for 1, okay? All right.
Wanna say that?
So again, this point here, we can label this while I'm here, this is 1, -2. And this value up here is 1, 1. I shouldn't say 1, 1, it's 1 undefined, but it's undefined at 1. Yep.
Is it -2?
So, what is the limit? Where does it go on the left and the right-hand side of 1? And what is the value? So if I draw a line, okay? Yep, my limit is 1, but my value is -2.
Oh, wait. And I'm a scholar.
A scholar, you are. A gentleman and a scholar.
A gentleman and a scholar.
Yeah, that's a rare breed these days. And yes,
Here I am.
how did we get what? E. Why is this the limit 1? Because remember, the limit is where it's going. So if my hands are this function, on either side of that dot,
Okay.
where the function comes to, this function
At 1.
connects at either side of that dot, right? That dot is where the function is headed.
Oh.
This is just a piece that was removed out of it, right? So I can't call this the limit because the function's not even touching this on the left or on the right. And I need to be tracking not the exact location, but where it appears to be going. That's what's important. Yes.
So the limit,
Yep.
it can be like an open dot.
Yep, yes.
When your limit is an open dot, that's
Uh-huh.
when you have, DME.
When my limit is an open dot, I do not have DNE. When my limit is an open dot, potentially my value is undefined. But what makes a DNE
This one they don't need.
is if I have my graph on the left-hand side going here and my graph on the right-hand side going here, and they're not touching. They need to touch for me to have a limit. So the only time I have a DNE for a limit is if I have a break in the graph or an asymptote in the graph that blocks me from even getting.
So if the,
Does that make sense?
so if the graph goes like through the point, it's not DMing?
If the graph goes through
Like
the
at
point,
one,
yeah.
it's like going through?
Yeah, if I can walk, like here, I can't get smoothly to this point. I have to jump down here to get to it.
So like
But
that
here, I
one
can just,
is-
step over that puddle and keep going.
You
So if
can
I can
just
just step
hop it,
over, yeah, then I'm good. If I have to jump or fly to get it to a different place, then I don't have a
So
limit.
it's
Yes.
not a limit.
Here's the back.
Yep. Okay, so let's go ahead and just discuss a couple of things, because I know that was our last question, so it was like you guys were looking into the future. When does a limit not exist? Yeah. What are limits? So we use them for continuity, in looking for continuity for, we have like a series of questions that we go through to determine if a graph is a flat or continuous. And those, if a graph is continuous, again, it tells us no breaks, no jumps, no holes. And again, it can be used for many different things, like tracking things. We can use it for, revenue and things like that, where I don't have any change in, a drastic change in what's going on with the function. In calculus, they do, if it's continuous, it is potentially differentiable, which means you can take a derivative and all that kind of stuff we're gonna get to as well. Okay? Yes? Yep. Okay, when does a limit not exist? There are 3 times that we discuss when a limit does not exist. The first one is when they don't meet. And we say, when the limit as x approaches a from the left is not the same as the limit as x approaches a from the right.
Oh, what, so I was writing it in words.
You can, yeah. This means
Wait, so what is it in words again?
when the left-sided limit isn't the same as the right-sided limit.
So when the graph doesn't flow.
If I want to do it visually, I could draw a little picture like that. That's when it doesn't, when they don't meet on both sides of that x value. But this is like kind of the definition way to describe it. When the left-hand side and the right-hand side don't come together,
So
they don't
touch,
match,
pretty much.
then, what's that?
When they don't touch.
When they don't touch?
When the graph, I put when the graph don't flow.
You can write however it makes the most sense to you, okay? When else does a limit not exist? Well, it's kind of the same thing as what I said in number 1, but it's not what we've discussed at all yet. And that is when there is an asymptote.
No, the graph has to go through. Like this. There's a line going through everything for that. No, like for this, the ones that have to go. They would have to do it.
And it has to be at the place that I'm looking. When there's an asymptote at x equals a, that means that I have a graph that looks like this. Here's my graph.
What is that?
Here is my any value a. That's what I mean by that. And I have this imaginary line that cuts through. We've seen those before. My asymptote is blocking my graph from crossing that location. So maybe one side of the graph, I'm going to do this in a different color so it stands out. So maybe one side of the graph goes up to positive infinity, and maybe the other side of the graph goes down to negative infinity. And so if I have an asymptote where x equals a, I can't have a limit because
They never get.
I can't get to that location.
Can't
Yep.
get to X, right?
Right, exactly. Now, when we do our 2 one-sided limits, I will sometimes refer to this as a limit going to positive infinity, and this other side is a limit going to negative infinity. And so we'll
They can
talk
never
about
touch each other.
that, but they will never touch each other.
Okay, now I get what
Yep.
she's saying.
Okay, good.
No, because
My last place
I'm learning.
is at an endpoint.
I'm learning. I first yeah.
Okay? And the reason that I don't have a limit at an endpoint is because I need to see where the graph is going from both the left and the right-hand side. When I have an endpoint, let's say I have an endpoint over here, do I have a left side? No. I have a stopping position. So it would look like this. Here's my graph. Here's an endpoint, and then this thing goes forever wherever it goes.
Yeah.
There is no limit here
Oh, because it's just gonna go right through it.
because I don't have another side.
Yeah, that.
I need to make sure it touches on both sides.
Yeah, it needs to be-
I'm missing this side. It's gone, I don't see it, I need to have that, okay? This is more of a kind of calc topic. We see that very little for our stuff here, but we'll practice it a little bit. In fact, we just have a few that we're gonna practice, we're gonna go through. We're gonna do the first one together, and then I'm gonna let you try.
Is this coming?
Everybody got it down? Let's see how we do. I want you to do A, B, and C right now. Again, we're gonna kind of do this together, but I want you to do A, B, and C and then stop and make sure that we're on the right, page here.
How much was it?
Yeah, go ahead. Help you. You don't have to ask. Help yourself. What's mine is yours, Arnett. I said what's mine is yours. Help yourself. What's that? Oh, excellent, excellent.
Yeah, but there's no other side, but it's coming from the right, so it's that one.
I put my answers up. Do I even have a left-hand side?
That's what I was saying. There's no left-hand side.
Here I'm looking at, I'm going to use my marker again. At -1, here's the left, here's the right. Okay? Do you see my left and my right? What's on the left?
Nothing.
Nothing. Yeah.
I thought the line was like where the two points meet. Like at one. Like I thought it goes here.
But we're looking at -1. I am interested at the location of -1. Yeah.
What, so why on the other one not the whole 2 points?
I'm not sure what do you mean by that. Let me go back to the picture. Why on the other one didn't it go to the two places where did it go?
And why is it not? Like the lines on there.
Yeah.
It's only on one side.
Yes, but that's because I have both sides here. I have a left-hand side, there's a picture on the left-hand side, and there's a picture on the right-hand side, okay? But on this particular graph, at -1, I have to look at x equals -1, because that's what I'm interested in. At -1, here's my line of interest. Is there anything on the left? No. So there's no limit on the left because it can't come from anywhere on the left. There's no part of that graph. If I'm going to add a piece, but I'm going to erase it because this graph doesn't have it, if there was another piece of this, maybe there was that line that continued, then I would have a left-handed limit, but I don't have that there. It's because the line doesn't continue on the left. Yep, because the graph itself doesn't continue on the left. Yep, yep.
So I was like, why would the right be one? Oh, because it ends.
Yep, because on the right-hand side, I'm coming towards this point, and it's 1. And that number is also the value. Yep.
So then for like looking at it and D, since that one's coming from, I mean, no. It was one of the,
Well, let's talk through D, okay? Because this one was like, wait, we didn't do anything like that. What the heck? Well, that's why I brought up the endpoints above this. So now I'm going to go to 1. So I erased all of my new wall. I'm moving on to D, E, and F. Here is at 1. Now I have it coming in on both sides because I'm looking at 1. So on the left, where is it going? Yes.
What's the difference between like f of -1 and like the limit?
This is the value, and this is where it looks like it's headed. And often they're the same, but often they are not. And so that's why we have two different things to describe them. I have what it equals at that location, and I have also what it looks like it should equal at that location.
But they're both below the x-axis.
But they're both about the y value on a given x.
You know what I mean?
So I'm always finding like the y value that corresponds to a given x position. Okay, yes.
A and B have to be the same for C to have.
No, it has, A and B have to be the same for C to have, for it to have a limit.
It's a little confusing on the
I didn't ask what the limit was as x approaches -1. If I did, if I asked you in general, what is the limit as x approaches -1, not from the left and not from the right, this would be does not exist. But this didn't ask limit, this asked value, and I need to separate those two. And that's why I sprinkle them in here and there on occasion, because they are two different questions, okay? So let's focus at 1. I already drew my line at 1. Here's a left side. Here's a right side. I want to look at the left-handed limit. If I'm going to be traveling on this function from the left and stopping at the wall of 1, where do I land? 1. Great. So that's my left-handed limit.
Wait, isn't it doesn't exist 'cause it's open?
But there's nothing
That's
on
the
other side.
value doesn't exist there. That's what we have to, again, separate, okay? Then I'm going to go here on the right-hand side. I'm going to travel along this function. Oops, I got to jump over that hole. Where am I headed?
Is it true?
2.
Oh my god.
Yep.
But it doesn't touch on the other side.
Do they meet? No. So this limit does not exist. Yeah.
How did we get to it, like, why didn't we start at like the open
Okay,
circle of
well,
one?
maybe we should. have some-
Because I need to, the whole, this tells me I am getting closer and closer to 1 from the positive side. So I'm heading towards 1 in this direction. So I'm following this graph from this direction. Oops, jump that hole, until I get to 1.
So it just
Where
has
does
to
it look
touch
like
on the
it's
side
going?
it's
Yeah,
coming from. not the
on
other
the side that it's coming from, where is it touching?
I
Yeah.
thought they had to meet,
That's if they have a limit, they have to meet.
but it says.
Yeah, but this is from the left.
Oh,
And
the
this is
left
from the
side's
right.
limit, bro.
And if these two values are not the same, then this does not exist. Yes.
So when like looking at this, like E, it says
Yep.
like limit of x to
Jeez,
y to the, from the right side of
From the right-hand side.
Should you just not look at the 1 there and just like start wherever on the right side
Yep.
to the 1?
Yep.
No? Okay.
Yes, and then get closer and closer and closer on the right, yeah.
Okay.
Okay, so now let's find the value of 1. What is the value? Yep, right here. How come? Because that's the closed dot, 1, 2. This is an open dot, 1, undefined. That means there's no value at that 1. And there can only be a value at one place or no places. Sometimes there are no values. This one has a place where it has a value, and that's the only place that has a value, so it's 2. Okay, let's try 2. Oops. Okay. So here's my line. Here's my left. Here's my right. Let's not talk value right now. Let's talk limit. What does it look like it's doing as it's coming from the left? It's going to 2. What does it look like it's doing as it's coming from the right? Do they meet?
Yeah.
Yeah. So from the left it's going to 2. From the right it's going to 2. Therefore my limit is 2. As long as those are the same, I have a limit. That's a definition of a limit, that it has to go to the same place from the left and from the right. But what is the value at 2? It's undefined. It does not exist. There is a hole there. There is no value.
There's no limit.
DNE stands for does not exist, typically used to represent a limit, that there is no limit at that location, it does not exist. Undefined means there is no value at that spot. You can't have a value. So, yeah. So if you put a DNE for this, you could argue that, yeah, it doesn't exist there. It really doesn't. And that's a fine. But we don't use undefined for this, for a limit. We always use does not exist for a limit. Okay? All right, let's do our 3. 3 is our next one here. Okay, I've got my eraser going on here. I'm making a mess of my sheet, but we can define that here at 3. I'm going to draw my line, my wall. I have a left side. I have a right side. Left and right sides are a struggle for me. I always have to make the L. I'm getting better at it, though. But So I have a left-hand side, I have a right-hand side. Talk to me about what this appears to be doing as it's coming in from the left. It's going to 2 again, another 2 answer. That's all right, I don't mind 2. How about where's it headed on the right? There is no right. If there is no right, it can't have a right. Does it have a value though?
Yeah.
Yeah, it's solid there at 2. It doesn't matter that my limit does not exist. I still have a value. So this is the 0.32. And so as I'm getting at the value of the function, it's the y value is 2. How about 0?
It's 0, right?
Yeah, what's my limit?
0.
It's 0. On the left, if I draw that line again, and I'm just going to do it in this red here, on the left it goes to 0, on the right it goes to 0, therefore my limit is 0. And don't worry about, because that's a continuous location on the graph, and a lot of people say, well, if I don't see like dots or holes or stuff happening, then I can't tell if there's a limit or a value. Yes, you can. It's continuous there, and there is, the value and the limit are the same. And a lot of functions have that. Linear functions, polynomial functions, when you graph your quadratics and things like that. Okay? Let's try a few again. This time I'm going to step back, and I'm going to let you guys kind of go full power through this and see if you can answer all of those, and then we'll compare and see how everybody does.
Okay, wait.
Okay, wait.
I'm confused though, like.
Yep.
I'm-
Correct your
So they're all
attempt
right.
and see how you did.
I just got a question.
Okay, hit me.
The infinity one.
Yes.
How does that work?
Well, that was stuff that you did in Algebra 2, and that's all about end behavior. What's happening to this? You could have just drawn lines and arrows. That's what you did in Algebra 2. You said it's going down on the left and it's going up on the right. That's all that's talking about. Well, what does it mean when it's going down? It means it's dropping to negative infinity. What does it mean when it's on the right going up? It means it's rising to positive. Yeah.
So to not beginning, you have to have both sides going.
Yes, you have to have them both come together. They have to touch. They don't have to touch at a solid place. They can touch at a hole, but they have to touch. Okay? All right, we've got a couple more. I'm going to do the same thing. I'm going to pause it. I'm going to let you guys try. Does anybody have any more questions on this before I move on? How do you feel? Is it working? Okay. So give that next picture a try and see how you do. Give it a whirl. Give it a whirl.
How do you do these?
Okay, give me 1 second. We're going to start tomorrow with that last one. So I want you to set that aside, and then we'll talk about that at the start of class tomorrow just to get our brains going. That'll be like our opener, okay?
I don't.